Now we're going to apply Ito's lemma to see how the differential of I behaves. So the differential of I includes the differential of V. Notice this is an important point that shouldn't be overlooked. Notice that in the portfolio, when we calculate the differential of the share position, we have to have a special term for the dividend payments. Namely, when we have N shares, we cannot say in this portfolio that NDS is the change in our position. NDS reflects the change in the price of the shares we bought, but it doesn't reflect the dividend payments that were made from those shares. So notice when we calculate the differential, we have NDS, but each one of our shares is also producing delta S dt in dividend payments. So again, it's the different. You always have to think about for the application at hand. Am I interested in a change in the per share price, or am I interested in the change in a position where I have already bought the shares? And so in this case, because we have a portfolio where we've already bought the shares, we need to add the dividend flows back into the differential. If all we cared about is how share prices change, we would ignore dividends. So that's an important concept. So then we have the differential of W. We use Ito's lemma in the usual way, and we write down this long expression. We notice that we have a couple of DS terms, two of them. Otherwise, all the other terms are DT. So if we're interested in making this portfolio risk-free, we would like to get rid of DS, because that's where the DZs are hiding. We don't have any other DZ terms in this expression, only in the DS term. So it now becomes apparent what to do. Why don't we just make N equal to minus VS? VS is the derivative of the option with respect to S. Well, that's the definition of delta. And if you go back to our earlier work, N, the number of shares we're going to buy in this portfolio, is negative delta. Notice that we're using a negative because in the binomial model we replicated the option with shares and T-bills. Here we're creating a risk-free portfolio with shares, T-bills, and the option. So the delta is a minus. It's like the hedged position of the market maker. With this value of N, we can now go back and determine what W needed to be. And again, this will look familiar from our original option pricing, that the value of T-bills is the value of shares minus the value of the option. And so now we have I equals 0 and DI is risk-free. So if I is 0 and DI is risk-free, DI has to be 0, can't be anything else. This goes back to an argument we made in an earlier module, and that is that if I have an initial portfolio which costs nothing, it's allowable for that portfolio to produce positive returns in the future as long as it also produces negative returns. That's a reasonable expectation. However, if I have if I have a zero investment that produces only positive returns, that's an arbitrage. If I have a zero investment with no risk, then the only way that can avoid being an arbitrage is for it to be identically zero in the future, just as it was in the start, because it's risk-free. And so when I collect this equation of DI, the coefficient of DT has to be 0. And when I do the algebra, I get the famous Black-Scholes equation. Again, how do I do that? I use the substitution that N is minus VS, and I use the substitution that W, therefore, must be equal to VSS minus V. And I simply put it into that equation, and I do the math, and that, what I find, is an expression times dt must be equal to 0. The coefficient of the dt, which is therefore 0, is this. And we've seen this before, the Black-Scholes differential equation. In an earlier application where we saw the Black-Scholes differential equation, I recall it did not have the delta, the dividend payment in it, and I should have mentioned if I didn't, that the differential equation of Black-Scholes can certainly be generalized to accommodate stocks that pay continuous dividends. So this is a little bit more general than the one we saw earlier, in that the coefficient of the VS term, instead of just being RS, is R minus delta S. This Black-Scholes partial differential equation, which is always referred to as a PDE, it's an equation that every contingent claim must satisfy. If you have a European, which means that it's only exercisable at maturity, every European style derivative on S has to satisfy this differential equation. Well, you might say, well, how can all prices of derivative securities satisfy the same differential equation? And the answer is the boundary condition, the terminal boundary condition. Different European, remember, a differential equation only tells you how the price function changes. What distinguishes one derivative security from another is that their payoff values at time capital T differ. Puts differ from calls, differ from other types of derivative securities that are European in nature. So it's the combination of the terminal value, the exercise value of the derivative, and the satisfaction of this equation, which uniquely prices the option. It gives us a unique price function. And the assumptions are that geometric Brownian motion is satisfied by the stock price, that we have a continuous dividend rate of delta, that the contingent claim doesn't pay any cash flows. We have a European derivative contract which you purchase, and then there are no payoffs, no cash flows until expiry. The interest rate's fixed. That's the R value. It's a fixed risk-free rate. And there's no transaction cost. That came up because, remember, we created an I, and the portfolio I ignored any potential transaction costs of its construction. We assumed that we could trade at some fair market price.